Welcome back, my dear students. Did you solve this problem? Did you get the answer in the same way? E is equal to 2.5 into 10 to the power 10 Newton per coulomb. Did you get the same answer? See what you have done. Did you substitute? Tau is equal to 4 root 3. P is nothing but 2AQ. 4 into 8. But here 8 is nano. So 10 to the power minus 9 centimeter 10 to the power minus 2. E sin 60. Sin 60 is root 3 by 2. If you substitute, you will get 2.5 into 10 to the power 10 Newton per coulomb. Next, you have to calculate what? Potential energy of the dipole. So, potential energy of the dipole is given by the expression PE is equal to, PE cos theta naught minus cos theta 1. Correct? Usually, for solving the problems, if we are not taking directly this expression, what we will do is, when it is making some angle theta with a uniform electric field, to calculate the potential energy, we usually take U is equal to PE cos of from 90 to cos of theta 1. So we take the cos of 90 to theta 1, where theta 1 is nothing but 60 degree, because this electric field and the potential will be taken normal. So when we take it normal from pi by 2, 90 to, see the electric field is like this. So we will take it as 90 degree. So therefore cos of 90 minus cos theta 1, where theta 1 is equal to 60 degree. Okay, so U is equal to PE cos 90 is 0 minus cos 60, or else U is equal to minus PE cos 60 minus 2AQ. 2A is 8. 32 into 10 to the power minus 11. Correct? E is how much we got? 2.5. Correct? Into 10 to the power 10. Cos 60 is 1 by 2. What is the answer? We get minus 4 joules. Are you getting the same? U is equal to minus 4 joules. From where to where? Theta naught to theta 1. It is actually electric field. If it is normal, then it is pi by 2. So we substitute from pi by 2 to theta naught. Therefore, from minus pi by 2 is 0. Cos 60 is half. Substitute, you will get the answer. Okay. Next problem. For all the solving problems, to calculate the potential energy of the dipole, you have to take initially this theta naught as pi by 2, from there to theta 1. Next problem. Two charges, 12 microcoulomb and 4 microcoulomb, are placed at 4,3 and minus 4,3. What is the work done in taking them from their positions to infinity? What is the question? Two charges 12 microcoulomb and 4 microcoulomb are placed at 4, 3 and minus 4, 3. What is the work done in taking them from their positions to infinity? So you have to take them from their positions to infinity. So what is the work done? You know what is the expression for energy or work done? U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. Correct? Q1 Q2 by R12. Use this expression and solve. Now initially they are placed in positions 4, 3 and minus 4, 3. Correct? If it is 4, 3 and minus 4, 3, what is the distance between them? See, I'll show you. If this is the center, from here to here it is 4. From here to here it is, for x-axis it is minus 4. So what is the total distance between the two charges? Total distance is 8. Correct? Total distance is 8. So we will take it as taking in centimeters. Okay. So then I can write 8 centimeter. Sorry, left to right. That is taking coordinates in centimeter. Coordinates in centimeter. So 8 centimeter. Now substitute 9 into 10 to the power 9 into 12 micro into 4 micro divided by 8 centimeter. What is the answer? We'll get it as 5.4. joules. Are you getting the same? 5.4 joules. This potential energy is nothing but stored potential energy is nothing but work done. From there, this is nothing but work done in taking them from their position to infinity. Earlier, while solving the derivations, we said work done is stored in the form of potential. So potential energy is nothing but work done. U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. When this is there, see coordinates 4 and minus 4. From the center, 4 and minus 4, the distance is 8 centimeter. So take the distance, solve it. Understood? Simple and easy. Next problem. Two positive charges (5 microcoulomb and 10 microcoulomb) are placed 10 centimeter apart. Find the work done in bringing them 4 centimeter closer. Find the work done in bringing them in bringing them 4 centimeter closer. Two positive charges are there, 5 microcoulomb and 10 microcoulomb. You are placing it at 10 centimeter apart. What is the work done to bring them 4 centimeter closer? That means you have to bring and close it, place it at 6 centimeter. What is the work done to keep it at 6 centimeter is the question. How can we solve this? Two charges, the value is given. So we will use the value by substitute in potential energy. 1 by 4 pi epsilon naught Q1 Q2 divided by R12. 9 into 10 to the power 9 into charges 5 micro into 10 micro. What is the distance? Initially 10 centimeter. What is the value of the potential at that point? Calculate. We'll get, I think, 4.5 joules. Are you getting the same? Take the calculator and solve. 4.5 joules. After moving them a distance, so potential energy in the system, if you move it 4 centimeter closer, what is the, for 4 centimeter, bringing closer for 4 centimeter, U is equal to 1 by 4 pi epsilon naught, charges are same, divided by 4 into 10 to the power minus 2. What is the answer here? What is the potential energy? In bringing them 4 centimeter closer, 9 into 10 to the power 9 into 5 into 10 to the power minus 6 into 10 into 10 to the power minus 6 divided by 4 into 10 to the power minus 2. What is the answer you get? I think we get the answer 11.25 joules. See what we have done? Earlier it was 10 centimeter. You have to bring and place it over here. So the distance is 6 centimeter by moving it 4 centimeter. Now you know for this full what is the potential energy. For this small distance, if you know the potential energy, subtract this full by the small distance, then what the value you get is for 6 centimeter, correct? So for this full, the distance 10 centimeter we have calculated. For this small distance, calculated. Therefore, subtract that potential energy minus this potential energy. So therefore, work done is equal to 11.25 minus 4.5 is equal to, what is the answer you get? I think 7. Correct? Nearly 7. Approximately 7 joules. Understood what we have done? We have taken and calculated for entire, then for this one, subtract full by this value. What the value you get for this one is the expression work done for the small value. So these are the problems to calculate potential energy or work done. Next, we will do one small derivation, that is expression for potential energy we used to solve the derivation for potential energies itself in this chapter, correct? But now what we are going to derive is, we are going to derive the expression for electric field on the surface of the charged conductor. expression for the electric field on a charged conductor in terms of surface charge density. We are going to find the expression for electric field now, not potential energy, on the surface of the charged conductor in terms of surface charge density. Let us consider a conducting surface. Okay, one conducting surface we have considered. On that conducting surface, we will imagine a Gaussian surface in the shape of a pillbox. We will place one Gaussian surface, pillbox, one box we have placed it, any box, we have placed one box on this conducting surface. Just like if this is a conductor, on that conductor we are placing a pillbox like this. So the surface is in contact and partially it is not in. See, partial it is contact, partially it is outside. So like this we have, this is a surface, upon that you are placing the pillbox, imaginary Gaussian surface in the shape of a pillbox of negligible height and small surface area delta S. Very small height and negligible surface area delta, negligible height and small surface delta S. Surface area delta S. Let E be the electric field. Inside the conductor, electric field is 0. On the surface of the conductor, field is normal. Electric field is normal on the surface of the conductor. Inside the conductor, electric field is 0. So here it is in contact with the charged conductor. There will be charges. Inside the conductor, electric field is always 0. Outside the conductor, that is on the surface of the conductor, electric field is drawn always normal to the surface. If E is the electric strength, then I can say flux. Phi is equal to E into delta S. You know that electric flux is phi is equal to E into delta S from our previous chapter. You know that sigma is nothing but surface charge density, is nothing but charge per unit surface area. Correct? So I will write instead of sigma, I'll give delta sigma in terms inside the magnitude. Sigma can be positive, sigma can be negative. Sigma is positive means it should be value should be greater than 0. If sigma is less than 0, it is negative. Okay. Magnitude of sigma is Q by delta S. Then I can say Q is equal to into delta S. According to Gauss law, phi is equal to Q by epsilon naught. 1 by epsilon naught times the net charge enclosed by the surface. So I can say phi is equal to sigma into delta S divided by epsilon naught. Equation number 1 and equation number 2. Equate equation number 1 and 2. From equation number 1 and 2, I can say E into delta S is equal to sigma delta S by epsilon naught. Delta S gets cancelled. So E is equal to sigma by epsilon naught. If E is greater than, E is equal to positive, then sigma is greater than 0. E is equal to negative, then sigma should be less than 0. So if sigma is greater than